Exponential models. Objectives: solve problems involving exponential growth, solve problems involving radioactive decay, carbon dating, and half-life, and use the compound interest formula. Applications of exponential functions. Exponential growth functions have the form a of t equals a sub o e to the kt, where a sub o is the initial amount present when the time equals 0. K is a positive constant that determines the rate or percentage of growth. When using the exponential growth model, you may be asked about doubling time, which is the time it takes for the original quantity to double. Exponential decay functions also have the form a of t equals a sub o e to the kt, where a sub o is the initial amount present when time equals 0. But here, k will be a negative constant that determines the rate of decay. When using the exponential decay model, you may be asked about half-life. That is the time it takes for a substance to exponentially decay to half its original quantity. Given a of t equals a sub o e to the kt, what is the doubling time? Doubling time is the amount of time it takes for a quantity to double in size. So we can figure out a formula for this. A sub o is my starting population size, e to the kt, and if I'm looking for the doubling time, then the amount at the doubling time is going to be 2 times the starting amount. Now let's see if we can solve for t to get the doubling time. If I divide both sides by a sub o, this will be 2 equals e to the kt. Then I can put this into log form. The natural log of 2 is equal to kt. Now, dividing both sides by k, I can see that the doubling time, t, is equal to the natural log of 2 divided by the constant of growth. I could also solve this formula for the constant of growth. If they've given you the doubling time, you would want to divide both sides by t instead. That way you would have k is equal to the natural log of 2 divided by t. So if they give you the doubling time here, you can figure out the constant of growth quite quickly this way. A bacterial culture starts with 250 bacteria. After 30 minutes, there are 600 bacteria. Let's find K, the constant of rate of growth. To start this, I'm going to start with the model A of t equals a sub o e to the kt. Now, a sub o is my starting number of bacteria, 250. E to the k, which is what I'm trying to find, and t, I'm given a time of 30 minutes and 600 bacteria that is tied to that 30 minutes. That is the amount of bacteria at 30 minutes. So this will be standing in for my A of t. Now I can divide both sides by 250. This gives me 2.4 on the left-hand side and e to the 30k on the right. Now I can change to log form. This will be natural log of 2.4 equals 30k. we can go ahead and divide both sides by 30, and that will give me my constant of growth. K is equal to the natural log of 2.4 divided by 30, which is approximately 0.029182 to 6 decimal places. Now let's write the exponential model of growth for the culture. The amount at time t will be my A sub O, which is my 250 starting, e to the k, which is 0.02918t. So we have an exponential model of growth where the independent variable is t in minutes. Now, when will the culture number 1,000 bacteria? We can use the model that we just made. 1,000 is our ending amount that we want, and 250 was the starting. Here's my K, my constant of growth. And when I'm looking at this, T is my variable that I'm solving for, the when. So I'm trying to solve an exponential equation. I need to isolate the e to its exponent. Let's divide both sides by 250. When I do that, I get 4 equals e to the 0.02918 t. Now I can go ahead and change this into log form. Now I need to divide both sides by that coefficient k. And t will be approximately 47.5. So that's 47.5 minutes for the culture to number 1,000 bacteria. Now, what is the doubling time for this particular bacteria? We know that the doubling time is going to be equal to the natural log of 2 divided by that constant growth rate. So when I put this into the calculator, I get an approximation of 23.75, and that 23.75, like everything else in this problem, is in minutes. The count in a bacteria culture was 200 after 10 minutes and 1900 after 35 minutes. Assuming the count grows exponentially, determine the following. Let's give our answers as exact values or round decimals to 2 places. First, what is the initial size of the culture? We really don't know by the information given because we were there 10 minutes into the experiment, and 35 minutes later, after the experiment started, the population was up to 1900. So what we need to do is a little bit of work to re-engineer this. Normally this would have been at 10 minutes we have 200 bacteria, and at 35 minutes we have 1900 bacteria. What we're going to do, since we know that the growth rate is true for any part of this model, is we're going to align to this time period at 10 minutes for our formula. So for A of t equals A sub O e to the kt t, I can say this starting amount was 200. E to the k, the other part that I have is at 35 minutes, we're at 1900. So if we're saying this is at the start of when we observed, the 1900 would have come 25 minutes later. So 25 minutes after this being our initial observation, the population is at 1900. This way we can solve for k and make some leeway in the problem. I'm going to divide both sides by 200. That gives me 19 halves on the left and e to the 25k on the right. Now I can change this to natural log form. This is the natural log of 19 halves equals 25k. Dividing both sides by 25, I'll have the natural log of 19 halves divided by 25. And putting this into the calculator, I'm going to get approximately 0.09. Now, when I make future calculations based on k, I'll use the full unrounded value out of my calculator just to avoid round off error. Now, let's start over again here. My a of t is equal to a sub o e to the 0.09005167119 t. So now I'm going to go ahead and put in what I know. I have a data point of 200 bacteria at 10 minutes. So I can fill that in. 200 equals a sub o e to the 0.09005167119, and the t that is tied to that a of t is 10. So that 10 and that 200 comes from that data point that they gave above. Right, now if I can divide both sides by the thing that is with the a sub o, then I'll have my a sub o by itself. So a sub o is going to be 200 divided by e to the 0.09005167119 times 10. And when I put that into my calculator, I get approximately 81. So the initial size of the culture was 81. What is the doubling time? Well, we know that the doubling time is going to be the natural log of 2, and we divide that by the k value that we just found. And when I put that into the calculator, I get approximately 7.7. So in 7.7 minutes, after 7.7 minutes has passed, you'll have double the amount that you started with at the beginning of that 7.7 minutes. Next, what is the population after 105 minutes? Well, let's go ahead and write what our model is. The model is a of t equals 81.27 e to the 0.09005167119 t. Now, if we want to know what the population is after 105 minutes, we're finding the amount at 105 minutes. Okay. Now when I put this into the calculator, I get approximately 1,038,436. So 1,038,436. Now, when will the population reach 14,000? Well, we can take the same formula that we've been using all along. 14,000 is equal to my 81.272 e to the 0.09005167119 times t, and then we can solve for t. So I'm going to divide both sides by 81.272 first. And on the other side, that will leave me with e to the k value. Now I can put this into natural log form. So this is natural log of 14,000 over 81.272 equals 0.09005167119 t. And when I divide both sides by that k value, I'm going to get approximately 57.18. So when will the population reach 14,000? That'll be 57.18, a time unit in minutes, just like the other times were in minutes. Given A equals A sub O e to the kt, what is the half-life? Now given A of t equals A sub O e to the kt, what is the half-life? Now the half-life is the amount of time that it takes for half of our original amount to decay. So when we talk about half-life here, it's a time. So how can we solve this formula for time to be able to find the half-life? Well, if I start out with an A sub O amount, e to the kt, then the amount at the time of half-life would be half of the starting amount A sub O. Now let's see if we can solve for t to find the half-life. If I divide both sides by A sub O, I would get 1/2 equals e to the kt. Now I'm ready to go ahead and change this to log form. This is natural log of 1/2 equals kt. Now I can divide both sides by k, and this is the formula for my half-life. T is the natural log of 1/2 divided by k. I could also solve from this point. So at this point, when we have the natural log of 1/2 equals kt, if I would instead divide both sides by t, then I could get my constant of decay, and it will be the natural log of 1/2 divided by the half-life. Here we have a medical isotope, technetium-99m. It has a half-life of 6 hours. How much is left from a 12-gram sample after 18 hours? So I'm going to show you a couple of ways to work through this. I know that at 0 hours I have 12 grams. That's what I'm starting with. If the half-life is 6 hours, that means that in 6 hours, this 12 grams will be cut in half to 6 grams. Now, if I let another 6 hours pass, I would be at 12 hours, and this 6 grams would be cut in half to be 3 grams. One more time, if I did another 6-hour time frame for this, I would be at 18 hours, and this would be 1.5 grams that is remaining. Now I'm going to show you another way, because if they wanted to know a number of hours that was not some multiple of the half-life, you'll need to have another strategy. So my half-life is 6 hours. Let's see. The constant of decay is going to be the natural log of 1/2 divided by that half-life of 6 hours. When I do this, put this into the calculator, I get approximately negative 0.1155245. Now, I can figure out the amount at 18 hours. It is the starting amount of 12 times e to the negative 0.1155245 times the time of 18 hours. So the amount at 18 hours, if we put this into the calculator, you'll get 1.5 grams. Let's suppose a chemical substance follows the nuclear decay model of y equals y sub o e to the negative 0.126 t, with t in seconds. Let's find the half-life. Well, we know that the half-life t is going to be the natural log of 1/2 divided by negative 0.126. When I put that into the calculator, I get about 5.5, and that is in seconds. The milligrams of medicine in the bloodstream after injection into a patient is given by A of t equals 600 e to the negative 0.035 t, with t in minutes. Find the amounts below. What is the starting amount of medicine? We can find this just by looking at the A sub O position. We know that we have 600 milligrams of medicine in the bloodstream at that time. What is the amount of medicine in the bloodstream after 1 minute? To find that, the milligrams of medicine in the bloodstream after injection into a patient is given by A of t equals 600 e to the negative 0.035 t, with t in minutes. Find the amounts below. The starting amount of medicine in the bloodstream. We know that is A sub O, and A sub O here is 600. 600 milligrams. What is the amount of medicine in the bloodstream after 1 minute? Well, we find that by finding the amount at 1 minute, just plugging 1 into the formula. When I put that into my calculator, I get approximately 579.36 milligrams. What is the amount of medicine in the bloodstream after 5 minutes? So we do similar as we did before, but it'll be the amount at 5 minutes. And putting that into the calculator, I get approximately 503.67 milligrams. Now, what is the half-life of the medicine? We know the formula for the half-life of the medicine is T equals the natural log of 1/2 divided by the constant of decay. When I put that into my calculator, I get about 19.8. That will be 19.8 minutes. We have two compound interest formulas that we'll cover in this section. We can calculate compound interest using the compound interest formula A of t equals P times 1 plus R over N to the NT, where T is the time in years, P is the principal, R is the annual percentage rate, and N is the number of times compounded in a year. This would be the formula to use if you're going to compound things daily, quarterly, monthly, yearly, and so on. So if it's compounded a finite number of times in a year. If we have an account that is using continuous compounding interest, then that formula is A of t equals P times e to the RT. P is the principal, R is the growth or interest rate per unit of time, and T is the time in years. Always, for either of these formulas, T is the time in years. So be careful if they've given you some time period like 6 months, then you'll be using 0.5 for T, not 6, because time for the interest formulas is always in years. Let's find the future value and interest earned if $56,780 is invested at 7.8% compounded quarterly for 15 years. So my principal is the amount invested at the beginning. My rate I'm going to record as a decimal, so that's 0.078. N is the number of times the money is compounded in a year's time. If it's compounded quarterly, that means it's going to be compounded 4 times in a year. And my time is in years, that's 15. So the amount of money in 15 years is figured by 56,780 times 1 plus 0.078 divided by 4 to the 4 times 15. Now, if I put this into the calculator, I get approximately $180,896.10. So the future value is that A of t that we just found, $180,896.10. And the interest earned is going to be the difference between that $180,896.10 and the original amount invested. Quickly putting that into the calculator, I get an interest amount of $124,116.10. Now let's find the future value and interest earned if that $56,780 is invested at 7.8% but compounded continuously for 15 years. Remember, that formula is A of t equals P e to the RT. My principal is the 56,780, e to the rate 0.78, time is 15, and this will be the amount in the account after 15 years. When I put this into the calculator, I get approximately $182,944.74. And that is the future value. So the future value is $182,944.74. And the interest that I would gain on this account would be taking $182,944.74, subtracting the original principal that was put in there, and we've then earned $126,164.74. In all, if we would invest in the continuous compounding account, we earn $2,048.64 more than we would with the account that is compounded quarterly for 15 years.